All right, so we're going to start with Chapter R, Algebra Bootcamp, and the very first topic is going to be evaluating expressions. So let's go ahead and review that skill. All right, to evaluate an algebraic expression means to substitute specified values into a variable expression. And right underneath this, we have three variable expressions. Each of them involve the variables x and y. And in the instructions, it tells us what they want x to be replaced by and also what they want y to be replaced by. It says find the value of each expression if x is equal to 3 and y is equal to -5. So basically, anywhere you see x, you're going to replace it with 3, and anywhere you see y, you're going to replace it with -5. Now, in most cases, once you do that, you're not finished. You do have to simplify according to the order of operations. So just something to keep in mind as we go along this. Our first algebraic expression is 2xy plus y squared. All right, so according to the instructions, we are allowed to replace x with 3. So I'm going to write this as 2 parentheses 3. Okay, anytime you're substituting, especially if it's negative, you might want to use some parentheses. As is the case with y. All right, so y is equal to -5. So put that in parentheses. And to this, we're going to add y squared, which is now going to be -5 quantity squared. So we will simplify from here on out according to the order of operations. You might remember that saying, please excuse my dear Aunt Sally, but have you heard of the saying, please end my day at Schoolcraft? Because that works for this as well. All right, but anyway, the P stands for parentheses, and that would really mean if we're adding or subtracting or multiplying or dividing inside a set of parentheses. And technically, that's not happening with what we have so far. So we would move on to the E part of this, which stands for exponents, and we definitely have one of those here. It's the power of 2. So we'll go ahead and work on -5 quantity squared. We'll leave the beginning part alone for now. -5 quantity squared is positive 25, right? And so that takes care of the E part. The M part of PEMDAS would tell us to take care of any multiplication that we're seeing. And there's actually a couple of rounds of multiplying that's going to happen because of 2 times 3 times -5. What I would do here is just go in order from left to right, doing 2 at a time. So for instance, I would first do 2 times 3 to give us 6 times -5 plus 25. And then, of course, we can do 6 times -5, which is -30 plus 25. And our final answer is -5. We did our first problem. That's going to require a... oh, I don't have the soundboard ready anymore. I'm doing a celebratory dab, all right? So just know that. So any questions about part A? All right, let's move on to part B. So part B is a little bit different looking, right? We have these vertical bars, and you probably know that those stand for absolute value. And absolute values can kind of be treated like parentheses where, if there's anything going on inside the absolute values, you'll want to go ahead and simplify that all down first, and then you can apply the absolute value operation. So in this case, we do have some stuff going on inside the absolute value symbols. All right, we've got 3x, which we can still use 3 to plug into it, plus 2 times y, which we can still use -5. And of course, the absolute value of whatever that comes out to be. So I'm going to kick this off to you. If you guys would take the next moment or two to simplify down the inside of the absolute values, I'll check in with you after that, and we'll move on. Anybody want to type in the value of the inside of the absolute values? So what you could do here is you can multiply the 3 and the 3 together. It'll give you 9, and this will give you negative 10. So the inside would look like 9 plus negative 10, which gives us negative 1. So now we can apply the absolute value. All right, what is the absolute value of negative 1? Yep, you got it, positive 1. So yep, that's what the absolute value does, right? It takes any number and just turns it into its positive. Positive will still remain positive, but if you have a negative on the inside of the absolute value, it becomes positive. And there we have it. Our answer is 1, and that's in honor of Schmitty Verbenmann Jensen from SpongeBob because he was number 1. All right, so let's move on to part C. This will be the last of the evaluating examples. We have x plus y all over 3 minus y. All right, so we're going to use the same values for x and y from the instructions. So we're looking at 3 plus negative 5 on top. And then on bottom, we'll have 3 minus negative 5. Now, when it comes down to it, and you have to simplify an expression such as this, you want to simplify the top on its own and simplify the bottom on its own. So in other words, we want to figure out what the numerator number is and the denominator number is. And then if there's any simplification after that, that's when we'll do it. All right, so on the top, we'll have 3 plus negative 5, which is negative 2. And on bottom, what's our number? So is the denominator going to be negative 2, positive 8, something else? Positive 8, you got it. Yep, double negative here. So this will actually end up being the sum of 3 and positive 5, giving us 8. And what do you guys think? Can we go a little bit further with this? You got it. Nailed it. Yep, so this becomes negative 1 over 4, since that fraction simplifies. Okay, so there we have it. How are we feeling? Rock on. Woohoo! Okay, so the next topic from section R.2 is going to involve exponents. Specifically, the laws of exponents. So there's going to be a little build-up before we get to those, though. Namely, a bit on notation. So I want to talk about what an expression such as this represents. It says here, if a is a real number and n is a positive integer, then the following expression represents the product of n factors of a. So essentially, this guy right here is going to be a number such as 0, 1, 2, 3, so on and so forth. And you can even define this for negatives as well. But that number that you have as a superscript tells you that there's going to be repeated multiplication of using the factor a, which I'll define that in just a second, what it's called formally. But it's basically an exponent, what n is, and it tells you how many factors of a you're going to be multiplying together. So generically speaking, a to the power of n is just repeated multiplication of a with itself until you've written out n factors of a, which I'm going to indicate that right below, n factors of a. Now a is going to be referred to as the base of this expression, and n is the exponent, or sometimes referred to as the power. Now, as an example of this stuff, I'll write it up here. That's my notation for example, by the way. If I had something like x cubed, okay, that power of 3 tells me that I should be multiplying 3 copies of x with each other. So x times x times x, right? And that would be the long form of x cubed. It works if your base is a little bit more elaborate. So for something like negative 2y squared, okay, since there's a power of 2 here, we could rewrite this as negative 2y times negative 2y, because that's what the 2 means. It means that you're going to be multiplying two factors or two copies of negative 2y with themselves. And sometimes it's actually easier to do a math problem if you expand it a little bit, or if you write it in its long form. So I'll let you know when it might be easier to do it that way versus some laws of exponents. But with that, that's a segue to the laws of exponents, which I'll summarize in the following table. And actually, maybe I'll have you guys start us out. Let's look at a to the power of 0. Any ideas as what anything to the power of 0 becomes? Exactly, yep. So this works as long as the value of a is not 0 itself. Okay, 0 to the 0 actually gets handled in a Calc 2 course. So we'll assume that the base a is not 0 when we see powers that are 0. All right, so as long as that's the case, anything raised to the power of 0 is 1. There you go. Now, in a lot of exponent type problems, they want the exponents to be positive in your final answer if there are any exponents remaining. So what happens if maybe one of your exponents is negative? That's what the next two boxes in this first row are going to address. To start things out, I want to write a to the negative n as being on top of 1. It doesn't change its value. Anything divided by 1 remains the same. But the reason why I'm putting the 1 underneath it is because of what we do to make this exponent positive. If we have a to the negative n on top of the fraction, so in the numerator, what you can do is actually throw it downstairs in the denominator, and by doing so, that will make the exponent positive. What happens with the 1? Well, that's going to move to the numerator. So basically, to make an exponent positive, you can do so by moving it to the other side of the fraction. So if that's the case, and we have a to the negative n in the denominator to start out with, this is going to move to the top, and the 1 is going to move to the bottom. Okay, so we're going to have a to the positive n on top now, 1 on the bottom, and this will simplify to simply a to the n. Now, what happens if we're multiplying two expressions with a base a that have different powers? Well, you can actually condense this into a single base a, provided that you add the two exponents together. So we can write a to the m times a to the n as a to the power of m plus n. So I like to say that multiplication turns into addition. Which that was probably a bad color to use. I'll do this one. So multiplication leads to addition. So in the next box, we're actually dividing, right? We have a to the m divided by a to the n. We can write that as a single base a, provided we do what with the exponents? What do you guys think? Subtract. Yep, you got it. So if it's division that's happening, then what you do is you subtract the exponents. Now, do note that the first exponent being used is the one from the numerator. Okay, and it's important to remember that because the order in which you subtract does matter. Okay, 3 minus 2 is not the same number as 2 minus 3. So now with the very last box in row 2, what happens if we raise something that has a power to a different power? So in other words, a power to a power, what happens is you multiply them together. All right, so we can still write that as a base a, and what we'll do with m and n is just multiply them together. Okay, so putting an exponent on something that already has an exponent just means you're going to multiply the exponents together. Now, anytime you have multiplication going on inside of a set of parentheses and there's an exponent on the set of parentheses, you can essentially distribute the power to each of these factors. Okay, so we're not only going to raise a to the power of n, but we're also going to raise b to the power of n. Now that brings me up to an anti-property. This will only work if it's multiplication or division, which I'll get to in a second. It does not work with addition or subtraction. So if this were a plus b to the power of n instead, we would not be able to distribute n to each of those variables. All right, so I'm going to say this is not equal to a to the n plus b to the n. All right, but if it is multiplication, you can distribute the exponent to all of the factors in there. And it also works for division. You can distribute the power to both the numerator and the denominator. So this would be rewritten as a to the n over b to the n. Last but not least, what happens if we raise a fraction to a negative power? Well, we have a couple of ways that we can start, and one way that we can start this is by distributing the power to both a and b. So we'd have a to the negative n over b to the negative n. And since those exponents are each negative still, we can kind of piggyback on the last two boxes of row 1, where we'll just move these variables to the other side of the fraction. So a to the negative n is going to go to the bottom, and that'll make n positive. And b to the negative n is going to go to the top, which will make n positive as well. So far, so good? Rock on. All right, so we'll do a couple of examples, and I'll answer any questions that you guys might have, and that'll be it for us for today. So it says here, simplify each expression. A little bit more though, express the answer so that all exponents are positive. Okay, so if we see any negative powers, we are going to have to, do the relocating to the other side of the fraction. So let's start with example part A. We've got the expression negative 3x to the fourth y to the negative 1 quantity squared. And the property that we're going to use to start us out with this is the first box in the last row, where it says anytime you have multiplication going on and it's all being raised to a power, each factor gets the power that you're raising the expression to. Now, there are actually 3 factors that you can form in the set of parentheses. The first factor is negative 3. Second factor is x to the fourth. And the third factor is y to the negative 1. So even though the property only has 2 factors, it does extend to 3 or more factors. So with that said, we can distribute the power of 2 to this negative 3, also to x to the fourth, as well as y to the negative 1. And here's how I'll write it out. Negative 3 quantity squared, x to the fourth quantity squared, and then y to the negative 1 quantity squared. Now once we do that, another property will kick in because, with a couple of these expressions, we're raising something that already has a power to another power. All right, and there is something in the table that helps us with that, and that would be this box. Okay, it says that anytime you're raising an expression with an exponent to another exponent, you just multiply the exponents together. So we have a couple of instances of that. For instance, we have x to the fourth squared. Okay, so we're going to have to multiply those together. And we also have y to the negative 1 squared. Now, what do you do with negative 3 squared? Well, that's just going to be positive 9, right? Now, x to the 4th squared is going to be x to the 8th, and then y to the negative 1 squared will be y to the negative 2. So far, so good? Are we finished, though? Like, is there a little bit more that we could do? All right, what could we do?
We can put the y -2 on the bottom.
Perfect, yep. Yeah, so you can consider this y to the negative 2 as being on top of 1, in which case if we want the negative 2 to be a positive 2, we'll have to just kind of like swap their locations, right? So this is going to be 9x to the 8th times 1 over y to the positive 2 power now. Now what I'm going to do next is write 9x to the 8th over the number 1. And the reason for that is so that this can now look like a product of two fractions, which technically it is. And here's where I get to remind you how to multiply two fractions together. In order to multiply two fractions together, and it also works with 3, 4, 5, 6 or more fractions, you simply multiply the tops together and the bottoms together. So you just directly multiply across and simplify, and 9x to the 8th times 1 is just going to be 9x to the 8th still, and 1 times y squared is going to be y squared still. And that's where the pain and torture, fun and excitement for this problem ends. Questions, comments, concerns, winning lotto numbers? All right, last one for us today. Going to be part B. We got 25x squared y all over 15x to the 4th y to the negative 2. So I included this example just to show you something that might be new. In both the numerator and denominator, you can form three factors. So for instance, in the numerator, one factor is 25, another factor is x squared, and another factor is y. And on bottom, first factor is 15, then x to the 4th, and y to the negative 2. And what's helpful about knowing that is you can take this single fraction and break it up into three separate fractions, as long as you're still multiplying them together. So here's what I mean. I'm going to make one fraction using just the numbers, so 25 and 15. So that'd be 25 over 15. That's going to get multiplied to a second fraction, which is just going to be built by using the x's, so x squared over x to the 4th. And that's going to get multiplied to a third fraction, which is going to be built out of using the variable y. And that's going to be y over y to the negative 2. Now let's work on simplifying maybe the first fraction. 25 over 15 reduces, since 5 goes into both the numerator and denominator. And when you divide both 25 and 15 by 5, here's what you're going to get, 5 over 3. And how do you think we might be able to handle our second fraction? Like, how could we simplify x squared divided by x to the 4th?
You can divide by like 2, basically. From like, I don't know if I'm saying it right, but the 2 becomes a 1 and then the 4 becomes a 2.
I gotcha. So maybe some canceling out or something like that?
Yeah.
Yep. Here's another way that you could do it. So if we look back in our table, we had this property here where it says if we're dividing by two expressions that have the same base, we can subtract the exponents. And you'll actually get the same answer if you do it your way as well. But I'll show it this way since it's referencing the laws of exponents table. We're going to write this second fraction using a single copy of x. And in the power of this x, we're going to subtract 2 minus 4. Okay, so remember, it's always the numerator's exponent that we write first in the subtraction. So we'll simplify that in the next step. But with regard to this third fraction, do keep in mind that if there's no exponent written, there still is an exponent there, and it's basically a secret Ninja 1, as I like to say. And we're going to do the same type of thing with our third fraction as we did with the fraction with x's. So for example, we're going to write this as a single base y, and we're going to subtract in its power 1 minus negative 2. Okay, so we subtract those from each other. And let's go ahead and simplify. We'll have 5/3 times x, and 2 minus 4 is negative 2, times y. Got to be careful here. We got some double negative action going on. That's actually going to make the exponent of y a positive 3. And like we saw at the last example, if there's still a negative power, in this case x to the negative 2, and then there's a little bit more that we can do, right? So let's write this as being on top of 1, and we can go ahead and switch the locations of these with each other. So that's going to be 1 over x to the positive 2 now, and then 5/3 in front of that, and then I'm going to write y cubed as y cubed over 1. And like we did with example part A, we're going to multiply fractions together. You just multiply across the tops and across the bottoms. So case in point, we'll have 5 times 1 times y cubed. So that's 5y cubed. And on bottom, we'll have 3 times x squared times 1, giving us 3x squared. And you'll notice that there's nothing really more that we can do. There are no laws of exponents that come into play anymore. All exponents are positive. There's just one copy of the variable y, or one expression involving y, one expression involving x, and 5/3 doesn't simplify. So this is all set and done. By the way, I cloud my final answers in just to make it pop. So you're welcome to cloud as well, or box, however you like to indicate your answer. You're more than welcome to stick with it. All right, but you'll see me using clouds.